Welcome back. So today we are going to continue our conversation about variation of parameters. It's part 2. We actually are going to do part 3. There is a lot to cover. So this is the second lecture on variation of parameters. I'm going to try to tie some loose ends, clarify a couple of things, and do an example. And for sure, we need to spend a little bit of time showing why did we use this system of equations? Where did it come from? Because without this, we couldn't have found yp. Remember, the particular solution was u1, y1 plus u2, y2. And we do need to know what is u1 and u2, and therefore we do need to know u1 prime and u2 prime from this system. So this is crucial. We need to know where it came from. But I will also show you a shortcut on how to go from here to u1 prime and u2 prime fairly quickly. Okay? So the first comment I want to make is this. If the coefficients of y double prime, which we generally call a sub 2 of t, if this is not 1, you want to divide across by a sub 2 of t. So this becomes a sub 1 of t divided by a sub 2 of t, a sub 0 of t divided by a sub 2 of t, and r of t divided by a sub 0 of t by a sub 2 of t, so that the coefficient is 1. This is called standard form. We like to write it in a standard form. Okay, this does not mean the coefficients are constants. It just means we're going to force. We have the right to force this to be 1, but free up the others as well, right? Free up the others and you don't lose any generality, okay? So, quick general example. I'm not going to do a particular one. What we did with this, we took this piece and set it to be 0, and we found y1 and y2, and hopefully using characteristic equations or something, we were able to find y1 and y2, and that is called the fundamental set or the building block, y1 and y2. These are functions of t, okay? That helped me build the general solution. So the homogeneous solution would be a multiple of y1 plus a multiple of y2 in such a way that y1 and y2 are not multiples of one another. Okay? And then we said the particular solution, and we just need one, we don't need more, and I'll explain that later. The particular solution is a multiple of y1, but this multiple is actually a function of t. So we could have easily written this u1 as c1 of t and c2 of t. But then it just makes life a little hard with the writing too many letters. So I just call them u1 and u2. Okay? So, and then what we did, in order to find u1 and u2, we used this system of equations, and from there we found 3 letters, w1, w2, and w. W was the Wronskian, which is basically the coefficients of the system. Your variables in this case are u1 prime and u2 prime. And the functions that you actually know are y1, y2, and therefore y1 prime and y2 prime. So we just look at the coefficients of my 2 variables, y1 and y2, and we found the Wronskian. We did the same thing here. We found w1 and w2. And after we found u1 prime and u2 prime, we had to integrate those functions to get u1 and u2 and hit them with y1. So my general solution is now YH plus YP, and YH is this, found already based on my fundamental sets, and YP is Y1 times the integral of Y1, of U1 prime, right? You found U1 prime, and dump it here, you get U1. We don't need to add a constant, and I'll explain, plus Y2, and then u2, but u2 is the integral of u2 prime, okay? Now, I want to show you a shortcut because there are so many steps in here. If you look at this system of equations that we actually used to do this, okay? You could set it up in such a way that you multiply matrices. I don't know if you're familiar with matrices, but if you take this 2 by 2 matrix, and this is a 2 by 1 matrix, you can multiply them if these numbers match, and the resulting matrix will be this 2 by 1. So we know we're going to get a 2 by 1 matrix. This is a 2 rows and 1 column. And the way we do it is we put the coefficients as a 2 by 2 matrix times my, multiplied by my matrix, my variable matrix, U1 prime and U2 prime, equals the resulting output, 0 and R of t. Let me take a quick break here and just go here and do something silly. So let's say I have x minus 3y equals 4, and I have 2x plus y equals 5, and I want to solve this system of equations. You could set it up in such a way that you write the matrix, the 2 by 2 matrix, which are the coefficients of x and y, 1, -3, 2, and 1, times my, let's call this matrix A, and times my variable x, which is composed of a 2 by 2 matrix called xy, equals my output. And if you remember how to multiply matrices, you do first row times first column, gives you the first row times first column. So 1 times x minus 3 times y equals 4. Here it is. And then 2 times x plus 1 times y equals 5. Here it is. And the reason this approach is better is because in order to find, so here is my product. In order to find xy, you need to get rid of this matrix A. Let's call it A, and this is x, and this is B. So AX equals B, okay? In order to get rid of A, you multiply A by A inverse. If you multiply A by A inverse, you produce unity, 1, 0, 0, 1. And since I multiplied A by A inverse from the left-hand side, I would have to multiply this B by A inverse from the left-hand side. And that's how you would solve for x, the matrix x, which is xy. So this will kill this. You get I, which just disappears, and you get this matrix B times A inverse. But you shouldn't write B A inverse. You should write A inverse B, okay? Because the order matters. The product multiplication is not commutative when it comes to matrices. And there is a shortcut on how to find the inverse of a 2 by 2 matrix without doing a lot of work. What you have to do is you flip-flop these. So let's say this is red, so it goes here. And then you keep these numbers where they are, but you change the sign. And then you divide by the determinant of the matrix. Determinant of the matrix is 1 minus -6, which is 7. So you just divide everything by 7. So this is A inverse. And I promise you that if you multiply this matrix by A, either way actually, whether you multiply this by this or you multiply this by this, you should get the identity matrix, which is 1, 0, 0, 1. Okay? So I'm sure you know this, but I just want to make sure in case. Now, so what I did, in order to find U1 prime, U2 prime, I have to multiply this matrix by its inverse on the left-hand side here. Not here, but here. So U1 prime, U2 prime will have to be the given matrix B times the inverse of this. And the inverse of this, flip-flop these, here they are, keep these where they are and hit them with negative sign, and then you divide each one of them by the determinant of the matrix, which happens to be W. So I just wrote 1 over W here. I don't want to divide by W, 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 W. I just put it outside, okay? Remember, W here is a function. It's not a number. What does that mean? It means U1 prime has to be this times that. And this times that gives me y2 prime times 0, which is gone, times plus negative y2 r of t divided by w. Here it is. The same thing with u2 prime. To find u2 prime, you multiply this by this. So this times 0 is 0. y1 r of t times divided by w. y1 times r of t divided by w. Basically, if you are given a function here, and you're looking for an ODE, and if you're looking for the particular solution, which means you need to find u1 prime and u2 prime, this is already given. You already found y1 and y2 from the homogeneous equation. All you have to do is find the Wronskian, and you're done. You can jump from there all the way to u1 prime and u2 prime. And of course, in order for us to find u1 and u2, you would have to integrate those two pieces and add them to the homogeneous, and you will be completely done. Okay? So one word on the Wronskian. So the Wronskian is the determinant of this matrix, 2 by 2, which is basically this. And so what I notice is this difference reminds me of the difference quotient. And the difference quotient looks like f prime g minus fg prime over g squared. And that is f over g quantity prime. So what I decided to do, I divided both sides by y1 squared. We assume y1 is not 0. That's one of the fundamental one of the solutions for the homogeneous, and that is just a quotient, a prime that is not supposed to be 0. The reason we shouldn't have 0 because we are dividing by w, right? We're dividing by w, so the Wronskian should never be 0. So I was thinking, okay, what happens if it is 0? Or let's push with this. Well, if this quotient prime is 0, that means the quotient is not a constant. That means y2 is not a multiple of c11, a multiple of y1. What does that mean? That means that's why we insist that these two solutions are independent, because if one of them is a multiple of the other, your w is going to be 0 and you're going to be in trouble. So that's why we want to make sure we verify that w is not 0. And hopefully, if you have the right choice for y2 and y1, and you know that they are independent, then you know w is going to be not 0 anyway. Okay, so that's a quick side note. I think it's helpful. So back to u1. So we found u1 prime and u2 prime. I'm going to copy these, and I'm going to integrate them. And the way we write this, of course, instead of writing r of t and dt, we're going to assume t is going to go from some initial time, t0, to some variable t. And therefore, I have to use my another dummy variable. I called it r of s. I called it s instead of t. So u1 is negative. I took the negative out. And y2 over w times r of t. y2 divided by w times r of s. And that is your u1. Now, this does not mean you'll be able to compute this integral, but we know it exists, right? This is how you find it. This is given. This is found from the homogeneous. The only thing you need to do is find w, which is the determinant of the matrix, and integrate, okay? The same thing for u2. You have y1. They look very similar, except that this one has negative y2, and this one has y1. So you write y1, r of s over w, ds, t0 to t, and this is your u1, and this is your u2, and hence, we know the solution. I didn't write it. Okay, that's okay. I thought I wrote it. Okay, so I'll write it here. So y general is yh, which is c1, y1 plus c2 y2. This is yh, okay, plus my particular solution, which is u1 y1. So I'm going to start with y1 first. y1 times, actually, because I have a negative. Yeah, that's fine. I'll leave it there. t0, oops. Oh my goodness. t0 to t minus y2 out of S over W ds plus y2 u2. And u2 is the integral from t0 to t, y1 out of S over the Wronskian ds. So this is going to be your general solution all the time. This is your particular here, and this is your homogeneous piece, okay? Sorry, it's a little messy. All right. Now, what I want to do now is work out an example. But this time I'm choosing, let's go back here. So far, since the course started, we used integer coefficients, okay? We haven't used functions of t yet, and we used the usual suspects, the e to the t's and the sine and the cosine and the binomials. I thought maybe I'll do now an example where the forcing function is not intuitive. So if I have e to the t, you guess e to the t. If I had e to the t and the homogeneous had e to the t, you guess t e to the t. If I had sine, you guess a sine t plus b cosine t. If I have the cosine, the same thing. If I had 5t, you would guess a plus bt. But if I have tangent t, then you cannot guess. So you have to do the work, okay? I picked the left-hand side to be nice. The second derivative is just the opposite of the original function, so you know it's going to be either sine or cosine. I use characteristic equations. Once you get the i's, you know it's trig. So y1 is cosine and y2 is sine. Notice that cosine and sine are independent. So we expect the Wronskian not to be 0. If the Wronskian is 0, we're in trouble. Because it would mean that they are dependent, which is not the case, or we made a mistake, okay? So my homogeneous equation is C1 cosine t plus C2 sine t. These are my this is the fundamental sets, okay? So now we're going to find the Wronskian because the integrals require me to find the Wronskian, right? So I'm taking this method now. I'm doing this method, okay? I'm not going to go back here. I'm just going to do this. It's faster, so I'm going to use this. Okay. So the Wronskian is 1 because it's just cosine squared plus sine squared. So I'm happy. I don't have to divide by anything. Notice that it is not 0, and it is expected because sine and cosine are linearly independent. So I'm giving you this function, and I'm just assuming t goes, this is in the first quadrant. T runs from 0 to pi over 2, pi over 2. So you could write the integral from 0 to pi over 2 eventually. So u1 is negative y2. This is y2. So you already know y2. You already know r of t, which is tangent of t. And w is 1. And therefore, you get sine s, tangent s, ds. From 0, I should write pi over 2 here. But that's okay. And I didn't want to waste your time. I have to use integration by parts. I got tangent s cosine s minus this integral. And then I had to find this integral. And eventually I found u1 to be sine t minus natural log of quantity secant t plus tangent t. That is just u1. Now, you may be wondering, why don't we just add c, right? Because when you integrate, especially if it is if there is no limit of integration, we add c. Why aren't we adding c? Why do we say we just have to find one particular solution and tag it onto the homogeneous and you'll be done? And I'll explain that in a second. u2 goes the same way. y1 is known. It's cosine t, okay? w is 1. Say thank you. And r of t is tangent of t. So I solved, and I got negative cosine t plus 1. So therefore, since the particular solution is u1, y1 plus u2, y2, I'm able to write the general solution. This is my homogeneous. Here it is. And my my particular is y1, y1, here it is, u1, this whole thing, okay, plus y2, u2. u2 looks a little nicer. Now, I don't know about you, but there is no way on earth I'm going to guess this function times cosine plus this function times sine. There is no way on earth I can guess this in order to say if I plug it in here, I'm going to get tangents. I don't know about you. I mean, if you do, you should just get your PhD right now. You don't need this course. So that's why we took time not to introduce the non-typical functions here. We only use exponentials, sine and cosine, and powers. Not power, but I should say polynomials, okay? So this is the very first time I picked a forcing function not to be one of those 2 or 3. And now you know why. It's just so ugly, okay? I'm gonna make a word. I'm gonna say a word on y particular. When you find y particular, okay, we said it's u1 y1 plus u2 y2. But let's pretend we're gonna say u1 plus some constants. Let's call it c3 times y1. Now y1 was y1. Plus u2, and let's say u2 is, instead of saying u2, but we're going to add the constants, because we always wonder, like, why aren't we adding the constants? Why do we keep insisting on the word a particular, one particular solution, okay? So that would be my particular solution if I had to add the constants. I use C3 and C4 simply because I had C1, I had C1 here and C2, so I don't want to confuse you, okay? Okay, so you can quickly tell there is a problem. Not a problem, it's like an overkill, because this is u1, y1, this one, plus u2, y2, plus c3, y1, plus c4, y2, right? But if you add this to the homogeneous, isn't that the homogeneous? Right? So it's just like an overkill. If you need $4, you don't need to have $5, okay? Do you have the right to have $5? Yes. Are you wasting your money, or like, are you just having more than what you need? Sure, you shouldn't. So just take the minimum that you need. And that's why we ask for one particular solution. One particular solution. Isn't that beautiful? It says if you have your homogeneous solution and you tag along one particular solution, you have found them all. That's the key, okay? All right. So now, I hope I didn't go too fast. Okay. I'll erase this. So now we're going to spend a little bit of time talking about the system of equation that we introduced last time. I just gave it to you and we worked out an example. We need to know where it came from. But let me just say a couple of words first. Let me erase this. We don't need this. Actually, precisely what I was saying earlier. In mathematics, you want to minimize the number of degrees of freedom. As I said, if you don't need $5, you just need $4, then just stick with $4. If somebody offers you a home for sale for $90, you don't offer more than $90. You're welcome, but you're wasting money, right? So let's say I'm just going to emphasize the importance of what we call without loss of generality. I actually used it today at the start of the lecture, without loss of generality. You probably have seen this concept. And in mathematics, mathematicians know this, so they just write WLOG. And everybody knows what it means. So let's say I want to prove some property about a triangle, a scaling triangle. And so you could say, okay, here is a scaling triangle. Oops, I don't know what's happened here. Here is a scaling triangle. And let's call it ABC. and you want to prove something about this scaling triangle, a random triangle. The problem, if you do this a lot in physics, you take some sort of a system and you dump it on a Cartesian coordinate system, right? So I don't know, you have a car or something, and you think that this would be better to put the Cartesian coordinate system here, so then you put it here, right? Or sometimes you put it here. You got to choose where to put your system to make your life easy. That's the key. If you just work like this, you're going to have these many letters to work with, right? You have 6 letters. So your degrees of freedom is 6. And can you do the math, whatever you're trying to prove about the scaling triangle, can you do the math with 6 letters? Maybe you can. The best case scenario, you're going to waste time. The worst case scenario is you can solve it, okay? So what do we do? Without loss of generality, what I can do is dump this line segment here on the x-axis and dump this point on the origin. This way, now my A is 0, 0. So now x1, y1 are not needed. I just dropped the number from 6 to a 4. And then, since you dropped this line segment on the x-axis, this y3 is 0. So now you went from 4 to 3. Of course, you have no rights to force x2 or y2 to be anything. They have to be random. Like B can be anything, right? It can go anywhere. You can move B however you want because you want the triangle to be scaling. So by forcing the point A to be at the origin and forcing the point C to be on the x-axis, you dropped your degrees of freedom from 6 to 3. That's 50% drop. And that just makes your life much, much, much easier. So anytime you can reduce what we call degrees of freedom, and you see this a lot in statistics. So we use degrees of freedom all the time, okay? Anytime you can reduce the degree of freedom by taking your system, whatever it is, a car, climbing or a triangle, dump it on some system, whether it is Cartesian or spherical or whatever, cylindrical coordinates, I don't care, to reduce your degrees of freedom, you'll be much better off. Okay? And that's why I talked about you don't need more than one particular solution. You just need one, okay? Feel free to have more, but you're wasting time. So let's spend a little time on this system of equations, okay? Because this is the thing that's helped me do anything I want, to find u1 prime and u2 prime, and that's how we found u1 and u2 by integrating. So what are we going to do? Obviously, we're going to have to go back here. This is my ODE. And you will notice I have double prime and a prime and the function y. And if I start differentiating, it becomes a nightmare. So we know the particular solution is u1, y1, u2, y2. Okay? And therefore, y prime, the derivative of this one, that's going to give me 4 terms because this is a product. So u1, y1 gives me u1, y1 prime plus u1 prime, y1. And this one also gives me 2 terms. If I go to y double prime, 4 term become 8s. 1, 2, 3, 4, 5, 6. This gives me 2 of them. 7, 8. This gives me 2 of them. And that is problematic. So what I decided to do, and that's what mathematicians have done, I underlined these 2 to remind myself. What I did here is I wrote this here, I dropped this here, and those 2 I put them to the end. So what we're going to do is we're going to force y1 prime y1. Did I say y1? I meant u1 prime y1 plus u2 prime u2 to be 0. So what does that mean? I'm not losing the general case. Without loss of generality, I can choose, I can pick, I'm looking for either, these are my unknowns, u1 prime and u2 prime. u1 prime and u2 prime. Did I make a mistake here? I should slow down. u1 prime, hold on. u1 prime, y1, and u2 prime, y2. Yeah, this is u2 prime, sorry. u2 prime, these two, okay? Actually, you'll remember them because they show up in the system, don't they? So, what I'm going to do is I'm going to pick either u1 prime or u2 prime. And then I'm going to choose, let's say we pick u1 prime. We just pick it. Then I'm going to choose u2 prime in such a way that this expression gives me 0. The reason we do that is because we don't want to deal with too many variables. Here are the variables that we have. You have u1, u2, u1 prime, u2 prime, u1 double prime, u2 double prime. That's 6. That's too many. So we're going to force this to be 0, and we're not losing, this is without losing the general case. We can pick y1 prime, let's say, and choose y2 prime so that this gives me 0 or the other way around. I can pick u2 prime, and then I'll choose u2 prime, and then we'll pick u1 prime in such a way that this is 0. So what does that mean? I put them in here, and when I differentiate one more time, this gives me 2 of them, this gives me 2 of them, and these, I'm just going to write prime. I'm also already forcing it to be 0. So basically, this is going to cancel, this is going to cancel, which is these 2, and that's 0, right? And when you differentiate that, you get 0. And that leaves me with, instead of having 2 terms, 4 terms, 8 terms, now I have 2, 2, and 4, okay? Because when you differentiate 2 terms, you get 4 terms, and that's gone. And that's the key. So now I have y2 prime, y1 prime, and I keep saying y1, yp, y prime p, y double prime p. 2 and 2 and 4, okay? So we're going to force that to be 0. Here are the first 2 terms. Here are the 2, the other 2 cancel. Here are the 4 that came from these 2. And the 4 here that came from these 2 were 0. So now it's time to plug in. So we know y double prime, it's this one, right? If yp is a solution, that means it fulfills the equation. So I'm going to write y double prime p plus a1t y prime p plus a0t y p equals r of t. That's all I did here. Here is a1t times y1 prime and then a0 times yp, okay? So what you notice is this. We know this is my homogeneous equation, if you remember. One of the solutions was y1, and the other one was y2. That's the fundamental set. That means if you plug them in here, you should get 0, right? For y1. So that's what I did here. So if you look at this one, u1, y1 double prime, if you plug in, let me slow down here. Okay, I'm going to plug in y1. So you get y1 double prime plus a1t y1 prime plus a0t y1 has to be 0. And the same thing goes for y2, right? Now, if you look here, here is u1. Don't let u1 bother you. Here is y double prime. Here is A1 Y1 prime, Y double prime, Y1 double prime, A1 Y prime 1, and then A0 Y1, A0 Y1, that's 0. And they all have a U1 in them, so U1 times 0 is 0. So the stuffing block is gone. Similarly, I could do the same thing with the blue. But if I multiply all of this by U2, then it's still going to be 0. So Y double prime of 2, U2, plus U1, U2 again, Y double, A1T, Y2, here it is, plus Y2, A2, A0T, here it is, times U2. So this blue is basically U2, the blue is U2 times this. And the stuff in black here is U1 times this. So that means that's 0, that's 0, that's 0, and that's 0. So that whole thing is gone. These two terms are gone. You're left with U1 prime plus Y1 prime plus U2 prime Y2 prime equals R of t. And that is my second equation. This is the one I forced, and this is the one I just got. And that's why this system of equation works. I hope you feel convinced to why this system of equation works. I hope you use this method from now on. It's a little better and nicer. I hope you understand why we don't have to add, once we find one particular solution that's sufficient. I hope you understand that these have to be linearly independent, otherwise the Wronskian has to be 0 and we will be in trouble. So next time, for part 3, you're probably going to guess what I'm going to do. Instead of picking a function that is ugly on the right-hand side, I could still pick that. It's no problem. I can pick a nice one like e to the t, or I can pick like secant of t. But what I'm going to do, we're going to work on what happens when these functions are not the typical, not constants. So let's say you have t here, or natural log of t here. What do we do with those type of ODEs? And that's, we're going to have to use power series then. So that will hopefully allow us to conclude the variation of parameters discussion, and that would be part 3. I hope this is helpful. I hope I didn't confuse anyone, and I'm going to assign some work, and have a nice weekend. Bye-bye.